Well, welcome. This is my presentation on the double inverted pendulum LQR controller. 1 second. Here we go. And so I chose this particular dynamical system because I thought it was interesting. I had not, as of yet, described it uh, in any controls class. Though of course we have done the single pole, the single link inverted pendulum, and so I was curious about this. I remember seeing a video online about with like a four link robot flipping up the links from the down position. So I wanted to know at least a little bit more. Though unfortunately this is not going to be as exciting as that. So a little bit of motivation about this system. Pardon me. The double the double pendulum LQR system is naturally unstable. We all know that, at least in the in the inverted position, like we are trying to control it, like we are attempting to control it within. It's underactuated, so it's not directly controlled by the at the joints. It's only controlled by the table or the cart, and that just results in huge amounts of chaos. Um, they're very highly unpredictable, and noise just creates makes impossible situations for us to be able to really get a hold of it. But it is possible to use feedback control to stabilize this thing, and so it will work. I will talk about this briefly. There are many other solutions besides LQR. LQR is just, of course, the method of obtaining a feedback matrix that operates to stabilize the system. But there are other ways of obtaining a feedback matrix. We learned about others in undergraduate control classes, and of course, there's tons of nonlinear and adaptive controllers, um, which other people use. But for our purposes, we will just be sticking to the linear case. And this is the dynamics of the system, which I found online, which I found online in the paper that I was analyzing. One of the difficulties of this particular uh, uh, design challenge um, is that most of the papers I found online actually were inconsistent, and actually had different equations of motion for the same system. Um, and there were many glaring errors I found out later in most of the papers I could actually find on this subject, which was very aggravating. But from what I've pieced together, these are the equations of motion. Um, at least for the second derivatives. This matrix on top is equal to this is equal to this business on the bottom in this form. And so we have to invert this M matrix um, in order to calculate the action in order to actually simulate our system. And so I did so, and I created this in a simple simulation package, adding it to the original one. And this is what that looks like. Pretty simply, just when it's not controlled, but it's just falling. And so you can see it just swings all over the place and goes into total chaos, much like well, much like actual two-dimensional two-link pendulums react. And then see the thing. Here we go. And one of the glaring mistakes I made at the beginning of this project was actually to only create in simulation the linearized equations of motion, which of course is a mistake. We need to put in the create, of course, the nonlinear equations of motion in order to make this project actually effective, which I did. Um, uh, and these after taking the Jacobian of the above differential equations that I just showed, and linearizing about the theta, all the thetas and the derivatives of thetas to be zero, um, we find these particular equation matrices equations of motion. Uh, and of course, LQR's purpose is to generate is of course to generate a feedback K matrix, which will minimize the constraints that we put on it for both actuation and state errors. And so I began the process of tuning this particular simulation. And one of the things I found from the paper that I read is that um, it turns out that using simply the identity matrix as the Q and the R, respectively, yields the best possible results. And I know, and it does sound counterintuitive, but I can't find, but as I'll show in just a second, I could not find any better combination uh, of Q variables and or R variable that yields a more stable or quick response to the commanded state to the commanded state. Um, so this particular equation yields this K matrix right here. These of course these last four controlling the theta state, and the first two controlling the x position and the velocity of x. And this is the first video of that in operation. And so it begins running, and you will notice that the block moves out of the way to the left and then begins moving to the right towards the commanded position of just one. And please forgive the slow simulation because of the inverse of the because of taking the M inverse. This is a rather slow simulation. And so, um, frankly, frankly, when I saw this for the first time, um, it felt a little fantastic. It looks, of course, right now that it's just a single link inverted pendulum, but it is not. It is a double link, as shown here with the two thetas and the z position. And as you can see, it can actually does converge with no steady state error. And in this particular case, it does not overshoot the trajectory. It does not overshoot the desired position, which is very nice. And even though that was slowed down due to the computational lag, that only took about 6 seconds to move over, which frankly, at least in my opinion, is pretty good. And here's a more in-depth analysis of this. Um, and as you can see, we're using very small forces, not very large, so we don't really have to worry about saturation very much, because we're trying to keep it from toppling over, and that window is very, very small. Um, but as you can see, it converges within about 5 to 6 seconds, and about takes about 10 seconds to like fully settle. Um, After changing things around, I messed around with some of the parameters. It turns out changing the thetas really doesn't do any changing the Q entries corresponding to the thetas does not really change anything. The only thing that that does matter are is the one corresponding to the control in the force input and the state, position, and velocity. And the and in this particular instance, as you can see, we completely overshoot our trajectory, which is very undesirable, just with this very small change, decreasing this one and increasing this one. And then the opposite happens with this one. I increased the x polynomial coefficient and decreased the force coefficient. But when that happens, it converges, but to half the value, which is the strangest result. I do not know why that is occurring, um, but anyways. Um, there are many limitations to this particular method. Um, the biggest of which is that this does not have the capability to swing itself up from the zero from the down position. Most papers that I read, uh, most papers that I saw require a sort of separate controller to like swing up that specifically control theta and not x position, and then they switch over to this. And those, of course, exist, but it was fascinating to learn at least about this part of the linearized and stabilized version of this project. So, thank you.